So we've seen a number of interesting reforms recently in the social sciences, and in particular in experimental psychology, that are geared towards addressing low replicability. And one in particular that I want to focus on today, from a statistical and methodological perspective, is the idea that you could conduct replications where you use multiple collaborating sites to all replicate a single published important finding. And so the idea is to try to reassess some of the seminal findings in the literature through these very large-scale and high-powered replications. As many of you in this audience probably know, several top journals in experimental psych are now explicitly trying to solicit these. It started with perspectives in psych science with the Registered Replication Report format. That is now moving to a new journal called AMPS. And so this is, these types of designs have really taken off in the last few years. So here's an example of a study that was recently subjected to a multi-site replication. So the original finding here is a classic finding in the judgment and decision-making literature about an effect called moral credentialing. So in a nutshell, the way this goes is that the idea is that people who recently had prior behavior that demonstrates that they are not prejudiced against some minority group in some way are somewhat paradoxically more likely in a subsequent opportunity to actually demonstrate behavior that may appear prejudiced. And so the reason for that sort of self-inconsistency is thought to be that once you have that initial opportunity to show that you're not prejudiced in some way, you've in some sense credentialed yourself to then behave more questionably later on down the road. And so the way that this original study looked at this effect was by directly manipulating whether subjects had an opportunity to credential themselves or whether they didn't. And so all the subjects read a series of statements that cast women in a negative light. For some subjects who were assigned to the credentialing condition, these statements were referring to most women. So you would get a statement like, most women are not really smart. For subjects who were in the non-credentialing condition, these statements would refer only to some women. And all the subjects have the opportunity to go through a list of these statements and either agree or disagree with them. So the idea is that if a subject is in this condition with the most women statement, they're more likely to view the statement as being sexist and so disagree with it. And in doing so, in disagreeing, they've established credentials as being not prejudiced. On the other hand, subjects who see statements that refer only to some women are less likely to disagree with them because they are less likely to perceive the statement as being sexist, and so therefore they've not established their credentials. So then the outcome of interest here was that at this point all the subjects rate what could be seen as a stereotypically male job description from a scale ranging from this job is much better for women to this job is much better for men. And so the prediction is that subjects who were in the credentialing condition, because they've already had this opportunity to disagree with statements, they've credentialed themselves to be not prejudiced, and so they're actually paradoxically more likely to rate this job description as being better for men. And so indeed, in this original study, that is what they found. This effect appeared to hold up. So then Charlie Eversole, who's with us today, as part of the Many Labs 3 project, did a multi-site replication of this effect in which they had 20 collaborating universities as well as one online sample on Mechanical Turk, each redo this experiment using a protocol that was quite faithful to the original. So what you're seeing in this plot is, so this orange, this red diamond here is the effect size of the original study, which is a correlation of roughly 0.2. And then each of these circles is one of the Many Labs 3 replication studies. And then in the top here, you have the pooled estimate, which aggregates over all of the replications and its confidence interval. So this is sort of an interesting story, because on the one hand, we have a pooled estimate that is in the same direction as the original, and it's statistically significant. But at the same time, the effect size is clearly much smaller than in the original. In fact, it's about 1/3 as large. And moreover, the replications themselves seem to be sort of all over the place. We have this cluster here that are in the right direction, but they're all pretty small. We have a couple that are even bigger than the original estimate. We even have several down here that are actually in the wrong direction. And so overall, the question that we want to try to address statistically is, did it replicate? The story is kind of complicated. So the analysis challenges that are posed specifically by these multi-site designs mostly have to do with the fact that many of the existing methods to analyze replication studies were really designed for settings where you have a single site doing a single replication. So even in a study like the reproducibility project, in that case we had one site replicating one finding times 100 studies. And the types of metrics that are statistically appropriate for those settings don't do as well when we transport them to the setting where we have this richer kind of multi-site data. So why is that? So firstly, I'll argue that metrics that were primarily designed for the single site replication case don't ideally characterize the scientific questions of interest in multi-site replications. And they don't really take into account the additional richness of data that we have there. Secondly, from a statistical point of view, these existing metrics also don't really account for all of the sources of statistical variability that come into play with these multi-site designs. And the problem with that is that this can actually lead, as we'll see, to conclusions that are overly pessimistic towards the original study. So we can end up with conclusions that make it seem like the replication was less successful than it really was. And we'll see that in a minute. So the first thing we wanted to do here was to distinguish between what we thought were really the main scientific goals of multi-site replications. So the first one is that you want to know, did it replicate? In the sense of, is the original study statistically consistent in some sense with the results of the replications taken as an aggregate? So what I mean by that is, in a case like the moral credentialing example, if we see an original point estimate that's X distance away from the aggregate of the replications, is that likely by chance, or is that inconsistent? Is that something that would not happen very often? Secondly, I think it's also useful to consider moving the focus from just whether the originally reported effect replicated to looking more broadly at the psychological effect under investigation, and to consider using these high-powered and unbiased replications to try to reassess evidence strength for the effect under investigation. So these are our two separate goals. In order to address them, though, we first have to consider some of the statistical problems and challenges that are raised by multi-site designs. And so this mostly comes down to the fact that there are many sources of statistical variability when you have many sites replicating one finding. So there are three in particular. So firstly, the original study has a finite sample size, and so it has statistical error associated with that. Secondly, each of the replications has a finite sample size and also has statistical error associated with that. Lastly, it's also possible that the true effects underlying each of the replication studies, as well as the original study, are actually not exactly the same as each other. So this is a form of heterogeneity. So the idea is that if Monet and his co-author conducted their study in 2001 and we replicate it in 2017, it's possible that the moral credentialing effect is not exactly the same anymore. It's also possible that my replication site may have a slightly different population from your replication site, and so therefore the true effect may actually be somewhat different. And so existing methods that are focusing on single site replications by necessity can't really consider in particular this heterogeneity issue. And that's because if you have one site replicating the finding, you can't really estimate heterogeneity. And so for that reason, existing methods at best account for 2 out of 3 of these sources of variability. In fact, what we see in practice as these multi-site replications become more mainstream, even when these replications are done in something like a registered replication report format, where you try to use exactly the same protocol in every site, you often actually do see some evidence that there's actually heterogeneity under the hood. So in one project, I think it was ManyLabs, it was a 2014 ManyLabs paper, first authored by Klein. I think it was maybe ManyLabs 1. Something like half of the replications there showed some statistical evidence of heterogeneity. And that's even with these very faithful protocols. The problem with this is that if you fail to account for all three of these sources of variability, what happens is that you basically are believing that the original study's estimate should be closer to the replications than it really should be. And the reason for that is there's noise due to these three sources of variability that you're pretending doesn't exist. And so in doing so, you end up with conclusions that can be too pessimistic towards the original study. The original study can appear to be more unlikely by chance than it actually is. So in order to actually correctly address these three sources of variability, the first thing that we have to do is to try to use the replications, which are hopefully unbiased because they're pre-registered and they have an analysis plan fixed in place. We want to use the replications to estimate the distribution of the true effects. So the distinction that I want to make here is that the true effects, even though the replication studies are unbiased, their estimates are not themselves true effects. That's because no replication study has perfect power. They all still have statistical error. So the data generating model here that we're assuming, which assumes normality of the true effects, is that we have some normal distribution like this of true effects, statistical parameters that are underlying the replication studies, with some mean that I'm calling M and some variance that I'm calling V. Then when we conduct our replication studies, study 1 and study 2, these have a true effect that's drawn from the distribution. And so my replication study 1 might not have the same true effect as someone else's replication study 2, but they're drawn from the same distribution. And then plus there's statistical error, where my study is going to get some point estimate that's not exactly hitting the truth, and someone else's is also going to get some point estimate that's not quite right. So the first step is so in order to use the replications to estimate this distribution, there are a couple of analytic possibilities. So this most simple one is just to get point estimates from each of the replications and then do something like a random effects meta-analysis. Another option that is generally going to be preferable, given that we have raw data, is to do something like a linear mixed model with normally distributed random coefficients as well as error terms. This is actually a form of IPD meta-analysis, as we heard earlier in Joshua's talk. And so having done that, that allows us to estimate the mean and variance of those true effects, assuming normality. Okay, so that gives us all the materials that we need to actually go back and address the two questions that we posed at the beginning. So firstly, to address statistical consistency, the way we frame this question is as follows. So if the original study estimated a true effect that is indeed drawn from the same distribution as the replications, then what is the probability that this estimate would be at least as extreme as what we truly observe it to be, if in fact it was the case that this is coming from the same distribution as the replications? So you can think of this probability as being sort of analogous to a p-value in the sense that if you have a large probability, that suggests that if I were to reach into that true effect distribution, draw a new true effect, and then have some associated statistical error with it due to finite power, that I would actually have a fairly high probability of coming up with an original study that looks like what I have. And so that would indicate relatively good consistency between the original study and the replications. In contrast, if this probability is relatively small, that would suggest poor consistency. It would suggest that it would be quite unlikely that I would see an original study like this if it's truly coming from the same distribution as the replications. So estimating this is straightforward once you have the estimated mean and variance of the true effect distribution. Without getting overly bogged down in notation, basically the numerator here is saying this is the distance between my original study estimate and the estimated mean of the true effects based on my replications, and the denominator is where we account for all three sources of variability. So that was talking about consistency between the original study and the replications. The next thing that we wanted to consider is how can we actually reassess evidence strength for the original effect that's under investigation. And so we posed two related questions. The first one is, I would say, sort of the most generous way to look at the original study. So we might want to know, we have this true effect distribution. What proportion of the true effects, so what proportion of real effects out there in the world are just at least in the same direction as the original estimate? I don't care about effect sizes yet. I don't care about whether it's close to the original estimate at all. Just what proportion of real effects are just in the right direction, regardless of effect size. Secondly, and more stringently, we might say, what proportion of the true effects are not only agreeing in direction with the original study, but are also stronger than some threshold of scientifically meaningful effect size? So we propose, just as a rough default, you might consider something like a Cohen's d of 0.2. So just saying, a relatively smallish effect size, what is the chance that the true effect is actually larger than that and in agreement and direction with the original? Surely this threshold would be dependent on the substantive thing that you're looking at, but this is possibly one default. And estimating this is, again, just a simple function of the estimated mean and heterogeneity of the true effects, as well as the threshold Q that you choose. And so here, if you're looking at the proportion of effects that are just in the same direction for the first question, you would have Q equal to 0. If you're looking at the proportion of effects that are stronger than a Cohen's d of 0.2, then Q would be 0.2. So just to give you some intuition behind how this works and why it's interesting, consider these two hypothetical distributions of true effects. So we have one that's less peaked with the orange shading and one that's more peaked with the gray shading. And then what I've done is this solid red line is a effect size threshold at Cohen's d of 0.2. And I'm shading the proportion of true effects that are indeed stronger than this threshold and in, let's say, the positive direction. So the difference between these two distributions is that the gray one has an estimated mean of 0.15 with relatively little heterogeneity. The orange one has an estimated mean that's almost at the null, only 0.02, but with much more heterogeneity. And so if all you look at is the traditional metrics, which would be something like the estimated mean and its confidence interval, you would probably say, okay, this replication has a pretty small pooled effect size, but maybe it's statistically significant. This has essentially no effect at all in aggregate, and this is probably not statistically significant. So that might lead to a relatively different view of evidence strength in these two sets of replications. On the other hand, if we consider the proportion of effects that are stronger than this threshold, we actually get just about 30% in both distributions. Why is that? It's because of the difference in heterogeneity. It's because this distribution is very peaked and this distribution is very flat. And so given that, we might say that, in fact, evidence, given heterogeneity, evidence strength for effects of scientifically meaningful magnitude in these replications is actually relatively similar between these two distributions, despite the fact that if you only look at the pooled estimate, you might end up thinking that it didn't replicate at all in the orange distribution. As a counterpart to those two questions, I think it's also useful to consider the proportion of true effects that are of scientifically meaningful size, but are actually in the opposite direction from what the original study investigated. The reason for this is that, especially when you have multiple sites replicating a finding, it may well be the case that there are settings where there's actually an effect in the opposite direction. And indeed, often when we design psychology experiments, we try to pit two competing theories against each other by saying, I'm going to design some manipulation such that if my theory is true, hopefully it will turn out positive, and if your theory is true, hopefully it will turn out negative. And so identifying situations where replications provide evidence for effects in the opposite direction can actually be substantively meaningful, in addition to shedding light on whether something replicated. And so estimating this is very similar to the proportion that are in agreement with the original effect, I'm just renaming the threshold Q star. And so this might be, for instance, a Cohen's d of negative 0.2 to look at a symmetric threshold that's on the opposite side of the null. So going back to the two distributions that we saw earlier, the interesting thing here is that although we previously saw that we had a roughly similar proportion of effects that are of scientifically meaningful size in agreement with the original study, and that was similar between these two distributions, if we look at evidence strength for effects in the opposite direction, we find that in one of these distributions, there's actually quite a large proportion, 30%, and in the other distribution, it's essentially 0%. So that's a relatively different view of evidence strength for potentially competing hypotheses or other reasons for effects that go in the other direction. So all of these analyses can be done with our R package called replicate. So as I mentioned before, basically the first step is to use the replications to estimate the mean and heterogeneity using either meta-analysis or something like a mixed model on the individual data. And then given that, you can calculate all the metrics that I talked about. We also have functions to analyze single-site replications, although I won't be talking about that today. So returning to the example that we saw before, so here I'm showing you just the basic metrics that you can get easily from the replication, and then I'm adding the new ones that I talked about today to see what more we can learn from that. So the original study's point estimate was a correlation of 0.2. The aggregated estimate in the replications is about a third as large. When we consider the consistency between the original study and the replications, we find that there's about a 10% chance that the original study would have estimated a correlation as large in magnitude as 0.21 if indeed it were drawn from the same distribution as the replications. So the interesting thing about that is that that's sort of not compelling evidence for inconsistency, despite the fact that the point estimates are quite different. And essentially that comes down to low power and also having accounted correctly for heterogeneity. If we consider the proportion of effects that are just as generously as possible in the right direction, we actually get 91%. So that's a fairly optimistic view of effects that are genuine effects of moral credentialing that are at least in the right direction. On the other hand, once we consider effects that are stronger than a threshold of a correlation of 0.10, which is comparable to a Cohen's d of 0.2, as I mentioned before, this drops to only 30%. So once we apply that threshold of a smallish, meaningful effect size, we start seeing that actually most of these effects are not meeting that criterion. And lastly, we're seeing effectively no effects that are strong in the opposite direction. So I think overall the picture that this paints is that perhaps we don't have strong evidence for statistical inconsistency between the original study and the replications, which is interesting given the huge difference in the point estimates. At the same time, evidence strength for effect sizes of moral credentialing that are of scientifically meaningful magnitude is considerably weaker than what we saw in the original study. So that's just kind of to illustrate what the picture that we can paint with these proposed metrics. Just a couple of quick extensions. You can actually also use this consistency metric to summarize evidence strength in a single site replication. Inherently, with single site replications, you cannot estimate heterogeneity, and so you just need to assume that that's 0. Additionally, some people actually propose that in addition to something like a registered replication report where all of the sites use the same protocol, it could also be interesting to consider conceptual replications where different sites implement, for instance, slightly different operationalizations of the same protocol or replicate, let's say, different studies within one published paper. These types of metrics can easily accommodate those without any modifications because they are taking into account the heterogeneity that is implicit in that kind of design. So just as a quick summary, we set out to deal with two objectives. So firstly, assessing statistical consistency, and secondly, reassessing evidence strength for the originally proposed effect. And we proposed metrics that address both of those. So the probability of an original estimate that's at least this extreme in the distribution of the replications, And secondly, the proportion of true effects in the replication distribution that are stronger than an effect size that's scientifically meaningful. So that's all I wanted to say. There's a preprint available if you want to download it, and that's how you can contact me. And I'm happy to take questions.
So maybe as a clarification question, but it sounds a little bit like a minimal effect test or an equivalence test if you do the, but then in a sort of meta-analysis. Did I understand that correctly? Or?
Yeah, so I think the goal is to really try to separate equivalence testing with the original, which is really getting at that first metric, consistency, from reassessing evidence strength using an effect size threshold that's not a function of the original study. And the reason for that is that they really are separate goals, and that you can have, for instance, a very low-powered original study that is equivalent in some sense to the replications, even if its point estimate is really far away. And that's just because its power is so low that it's consistent with almost anything. But at the same time, if you pick an effect size threshold that's not chosen based on the original study, like Cohen's d of 0.2, you might have quite weak evidence in the replications to support that.
Could you say anything about how many replications you would need for that? Because I think many people would just maybe internally replicate a study once, while I think your estimates rely on the fact that you have quite a large number of replications. So yeah, I would just like to.
Yeah, that's a great point, especially because one of the interesting statistical issues with meta-analysis more broadly is that estimating the heterogeneity is really hard. It takes a lot of studies. So even if you have huge sample sizes in each study, it's really about the number of studies. So I would suggest roughly that you need about 10 in general replications for these metrics to be sort of statistically stable. That becomes especially important when you consider confidence intervals for these metrics, which the package will calculate, but those in particular are going to depend on having more than about 10 replications to get stable estimates.
Could you talk about the role of the assumptions about the distribution of the true effects and how you kind of recommend going about thinking about the sensitivity of the results of those assumptions?
Yeah, that's very important. So, I mean, one good thing, so it's definitely an assumption. I think there are cases where, so for example, there was a replication study about anchoring effects where it really looked like the estimates themselves were not at all normal. They were very highly skewed. And so that's a case where probably the true effects are also not normal. So I think the first thing I would do is look at the distribution of the replication estimates. Although those are not the same thing as the true effects, if the true effects are normally distributed, then the replication estimates should also be normally distributed. So if you're seeing something very skewed, I would not try to apply these metrics. But yeah, that is definitely an assumption that's implied here. And it's also another reason that you need more than a tiny handful of replications, because otherwise you really can't assess whether that assumption is reasonable.
Are there extensions of your quantities of interest for other kinds of distributions that might be typical?
Not yet, although I think it's an interesting direction that I'd like to consider, but not yet.